In this part, we will explain Model 7.5 in Chapter 7, Plane Wave Propagation, in the textbook Fundamentals of Applied Electromagnetic. This model shows the wave attenuation. So there will be electromagnetic wave, electric field and magnetic field, propagate in different materials, 3 different materials. Okay, so first one with low conductivity, 10 to minus 3 Siemens per meter, so it could be considered slightly loosey. Second one has 1 order higher conductivity, so it's 10 to minus 2 and it's considered moderately loosey. And the third one, or last one, it has conductivity 1 Siemens per meter, so it's considered highly loosey. The applied electric field, it has 10 volt per meter as amplitude, maximum amplitude, and the frequency 10 megahertz. So this electromagnetic field or this electric field will be applied in 3 examples or in 3 materials. So let's start. So first here, the electric field in blue line and magnetic field in red line, and magnetic field in blue line propagate, travel in Z direction. So the electric field, let's say it's in X, and the magnetic field oscillated in X, and the magnetic field oscillated in Y. Okay, and the maximum here it's 10 volt, so according to that the maximum of the magnetic, it's about 8 to minus 2, 8 multiplied by 10 to minus 2.08, that's mean ampere per meter. And both of them attenuated, okay, experience attenuation, okay, and this attenuation increased with Z. Okay, so at the position when Z is equal to 1.6 lambda, okay, the amplitude of E is degraded to what about 0.36 of its maximum, that's mean at about 3.6 voltmeter, 36%. So this position is called penetration depth, delta, or skin depth. Sometimes it's called skin depth or penetration depth. So at this position, the amplitude of the field, magnetic or electric, okay, degraded to at about 36%. In terms of the power, here we have power density, which is equal to the multiply or the product, between electric field and magnetic field. So in terms of the penetration depth will be shorter, okay, and the degradation is faster than the degradation in case of fields. So here the penetration depth is equal half to penetration depth when we are when it's calculated in case of field, and that's because of course the power proportional with the electric field as proportional with the square of the electric field. So the power proportional with the square of the electric field, or we can say power is equal to electric field square. Okay, so it will be attenuated faster, okay, and the penetration depth will be shorter. It's half of the penetration depth here. So in this example, the penetration depth is equal to 1.6. That's mean here we have penetration depth, it's about 0.08 of lambda. Okay, that's mean the penetration depth is 1.6 of the wavelength of the 10 megahertz inside this material. Okay, inside this material. So here penetration depth is equal about 16 meter. It's about 16 meter. Okay, notes the distance from here to here, it's about 6 lambda, so here we have about 1.6 of lambda. Maybe here 2, 4 and 6. Okay, so let's change the material and see what will happen in the second example where the conductivity is 0.01. In this case, what we expect the attenuation will be more stronger than the first one, because here we have material with higher conductivity, so we expect more attenuation and we expect shorter penetration depth, and that's what we'll get here. The penetration here is about 0.2 of lambda, 0.25 sorry of lambda, so it's equal 2 meter. In first case it was about 16 meter here, because the increasing in the conductivity, the penetration depth is reduced to be 2 meter. Okay, that's because the material is considered moderate loosey material, or it has conducting properties more than the first one. Let's go to the third example or third media. Here we have highly loosey material with conductivity 1, so the penetration depth is reduced to be 0.16. That's mean 16 centimeter. Okay, so 100 times maybe. Okay, it's 100 times because here we have 16 centimeters, so if we multiply by 100 it will be 16 meter as in this example here. This is 15.9, it's about 16 meter. Yeah, so 16 meter, and here we have 16 centimeter, so it's sorry 100, yeah, because 100 times shorter than the first example. So here we have very high attenuation, very high attenuation in this example, because we have higher conductivity, so here we have same electric field in traveled in 3 different material, and we saw the difference. The first one, the electric field and also the magnetic field propagates inside the material, okay, with distance longer than the other two, where the penetration depth here is about 16 meter. So the electric field lost what about 65 from its maximum power after 16 meter. Okay, so after 16 meter inside the material, the electric field attenuated about 65% from its amplitude. In the second example, okay, it lost same percentage, 65 from its amplitude, but where after about 2 meter. In the third material, okay, this energy is attenuated after just 16 centimeter. Okay, so here we have same electric field but different materials, and in each one or through each one the attenuation was different according to the amount of the conductivity.